Dear respected viewers, in today's session, we will have a look at AD converters, which are based on SAR type, that is successive approximation register. Now, what SAR type analog to digital converter means, we will have a look at the internal general internal diagram of it. And in this diagram we can see we have a control logic. It is similar to the general diagram that we have already seen earlier. Here the control logic is having one input called start, which is usually the start of conversion. Then we have the clock. Then we have end of conversion. This will be activated when the conversion is complete. Then we have a register. This register is the successive approximation register. We will have a complete discussion on successive approximation register in a while. Now, the output of this register is connected to a digital to analog converter. Now, the output of this is VAX, which is continuously compared with the unknown analog input, which is VA, and it has been compared with a comparator constructed out of an operational amplifier connected in open loop configuration. Now, when we are talking about A to D converters, it is actually it starts working when we provide a start of conversion signal to it. And as we all know, A to D converters are very slow, and when they are connected to high speed devices such as microprocessors, microcontrollers, the data transfer is not done efficiently. And in order to do the data transfer done efficiently, we need to go for asynchronous data transfer. Now, what is asynchronous data transfer related to AT2 converter and microprocessing or microcomputing systems? When A to D converter is connected to a microcomputing system, the A to D conversion will start when it gets a start of conversion signal. Now, it starts to convert the signal, that is the unknown available analog input is getting converted into its equivalent digital output. So it will take a fair amount of time. During that time, the microprocessor will get back and do its own work. And when the conversion is over, the A to D converter will generate an end of conversion signal, which will then again trigger the microprocessor or the microcomputing unit to stop its own work and accept the converted digital data into its own data bus. And this is how the asynchronous data transfer is carried out between an A to D converter and other microcomputing systems. Now, let us have a look at the process flow of SAR type analog to digital converter. Now, we can see the output of the SAR is initially cleared, and the process starts with the most significant bit of the successive approximation register. So when the start is initiated, the most significant bit of the successive approximation registered is set to high. Now, the output of the DAC, which actually is taking the input from the successive approximation register, the output, that is the VAX, is continuously compared with the unknown voltage VA. So if VAX, that is the output from the DAC, is greater than the unknown analog input voltage, then the bit which was set initially at the output of the SAR will be reset back to 0, and the next bit of the SAR will be high. Now, this process continues till all the bits of SAR are compared. So, after the process of comparing all the bit combinations of SAR, finally we will get the desired digital output for the unknown analog voltage that has been given at its input. Now, we can understand this by just a simple example. Now, before we move on into this particular example and try to understand how it works, let us first assume that an unknown voltage VA has been given at the input of this A to D converter, and the expected output is, say, it is 11010100. Now this is an assumption, and we are taking the assumption just in order to try to understand how this particular SAR works. So again, I am repeating, we are assuming an unknown voltage VA that has been connected at the input of this A to D converter, and there is a assumed output, there's a trial output that is 11010100. Now I'm considering this because we have considered A to D converter which is having an output of 8 bit, that is a 1 byte. It's a 1 byte A to D converter. Now let us see what happens. Now we assume that a start of conversion has been already given to the control logic. Clock is already running inside the A to D converter. Now, as per the SAR process flow, the most significant bit, you see, the most significant bit has been set to 1. Now, this value, this digital value that is presently is the input to the DAC will provide a VAX. Now you just have a look at this digital value with the trial digital value. Now the trial digital value is greater compared to this. So the voltage at the output of this VAX, that is VAX, will obviously be less than VA. So in this particular situation, we will hold this to 1 and proceed for the next bit. So you can see at the first location, at the first step, this is the initial step, the output of SAR is 1 and it will be kept 1. Now let's move on to the next step. Now in the next step, the next bit of the SAR is set, and again this particular digital value is compared with the trial value. So again we can see the trial value has a greater value compared to this. So again VA will be greater than VAX. So again in this particular situation we will retain this 1 and move to the next situation where we will again set the next bit to 1. Now let's move to the next step, step number 3. Here we have changed this bit from 0 to 1. Now you compare this with the trial digit, the trial digital output. Now we can see the output of the SAR is now greater compared to the trial digital output. So now the value of Vx is obviously greater than Va. So this is the situation where we now have to reset this back to 0 and go to the next bit and set it to 1. So on the third step, you can see we are presently at this particular juncture, and here the comparator output has gone to the reverse since Va is less than Vax. Now go to the next step, step number 4. We have reset this bit to 0 and the next one to 1. Now again we will compare. Now when we compare, again the trial output is greater compared to this. So Va is greater than Vax. We will hold this pattern and then move to the next by again setting the next bit to 1. But now if we compare, we can see Va is less than Vax. So following the procedure, we will make this 0 and set the next bit. We have reset this and set the next bit to 1, and then again we will compare. We see that the next bit, when we increase it to 1, it has now gone beyond this, and now Va is less than Vax. So as per the procedure, this will be 0 and the next one will be 1. So when we do that, again this has gone greater compared to the trial output. Now as per the procedure, we will reset this, and this ends the comparison state, as we have compared all the 8 bits of the SAR. And now you can see the value at the output of SAR is equal to the trial output. See, this is 11010100. Trial output that was required was 11010100. So this is how an 8-bit SAR type AD converter functions. You can just see one thing. The actual value of this was received in this particular state, but the procedure went on, and in this particular type of a device, all the 8 bits will be first compared, and only then the final result will be accepted, and only after that the end of conversion will be generated. So to conclude, we had a very brief discussion on the very brief outline of the A to D converters. We had a discussion on the nature of A to D converters. These are slow compared to high-speed devices. Then we had a discussion on the process flow of SAR type A to D converters. Then we had AD converters. We had a discussion on AD converter with the successive approximation register with proper illustrations. So thank you for watching this video. In our next video, we'll try to take up R2R ladder network, which is a digital to analog converter. So thank you again for watching this video.